The universe as we currently comprehend it, stretches unimaginably across the vastness of space, a seemingly endless sea filled with billions upon billions of stars, galaxies, and very likely planets. Our best instruments and telescopes have enabled us to observe incredible distances, peering into realms that once existed billions of years ago. But even with all our technological progress, what we see might only be a sliver of what truly exists. It's entirely possible, perhaps even probable, that beyond this observable slice of the cosmos lies an even greater, unseeable region, possibly part of a massive multiverse. Despite all the remarkable scientific progress we've made and the countless pieces of data we've gathered, one question continues to haunt humanity: are we truly alone in this vast expanse? We've scanned the skies, analyzed distant atmospheres, probed the surfaces of planets and moons, and yet, not a single piece of definitive evidence has surfaced that points to life beyond Earth, not even something as small as a single-celled microbe. For all the intelligent guesses and educated assumptions scientists have made, the truth is, we simply don't know. The range of possibilities is staggering. Maybe life is abundant, scattered across the galaxy, waiting for us to develop the right tools to detect it. Or perhaps Earth is a rare exception, a cosmic miracle where the improbable conditions for life somehow all came together. Both ideas are equally compelling and equally unsettling. The only way to truly answer this cosmic question is through a significant leap in our understanding. But that naturally raises another question. How exactly do we plan to reach that level of understanding? What steps need to be taken, what technologies developed, and what data gathered to finally determine whether or not we're alone? To start making sense of our current situation, it helps to divide everything we know into three distinct categories. The first category includes things we know to be true, based on solid, repeatable scientific evidence. The second covers things we assume to be true, based on our most up-to-date models, simulations, and logical conclusions. And finally, the third includes everything that remains unknown, questions we don't have the answers to yet, sometimes because we simply haven't developed the tools to even ask them properly. So let's begin by focusing on the things we know with confidence as of the year 2023. These are facts grounded in observational data, experimental results, and theoretical predictions based on well-tested scientific models. They're not guesses or speculations, but solid cornerstones of our current understanding. Over the past 3 decades, humanity has achieved a dramatic shift in its cosmic knowledge. In the early 1990s, we didn't even know if other stars had planets. Today, thanks to missions like Kepler and TESS and ground-based observatories equipped with advanced spectrometry and imaging techniques, we've confirmed thousands of exoplanets and have rough estimates suggesting there could be trillions more. Within our own galaxy, the Milky Way, there are estimated to be about 400 billion stars. That number alone is mind-blowing, but what's more, the Milky Way is actually a relatively large and evolved galaxy when compared to the typical galaxies scattered throughout the universe. It's mature, rich in heavy elements, and diverse in terms of star systems. We now understand that stars can be categorized by mass and temperature into specific types: O, B, A, F, G, K, and M types, with G-type stars like our Sun being among the most hospitable for life as we know it. About 3 to 5% of stars in our galaxy fall into this G-type category, while 15 to 20% are K-type stars, which are cooler and less massive but still potentially life-supporting. The vast majority, about 75 to 80%, are red dwarfs or M-type stars, which are smaller and longer-lived but often flare violently, posing challenges for planetary habitability. Then there are the rare, massive blue stars, which are extremely bright but live only a short time, making them less likely candidates for hosting life-bearing planets. We've also learned how to analyze a star's metallicity, its proportion of heavy elements beyond hydrogen and helium. This measurement is crucial because it directly influences a star's ability to form rocky planets. Statistically, stars with higher metallicity, at least about 25% of the levels found in our Sun, are far more likely to host planets that are rocky and Earth-like. Remarkably, around 98% of all known planets orbit stars that meet this metallicity threshold. Those that don't make up only about 2% of known planets, indicating a strong correlation between heavy element abundance and the likelihood of planet formation. Putting all these facts together, astronomers have been able to estimate that there may be somewhere around 10 to the power of 19, or even more, potentially habitable rocky planets in the observable universe. These are planets that lie within the habitable zone of their stars, have a solid surface, and could, at least in theory, harbor some form of life. If our technology were advanced enough to examine all of them directly, but still limited by the laws of physics, we might be able to detect signs of life from Earth. But since we currently can't, we have to rely on assumptions to guide our research. The first and perhaps most important assumption is that life arose on Earth naturally, through a process called abiogenesis, where simple chemical compounds eventually gave rise to complex, self-replicating organisms. If this is true, then any planet with similar conditions and chemical ingredients might also be capable of producing life. This doesn't mean the life will be exactly like ours, it could be very different, but the basic principles would be similar. Another assumption is that the laws of physics we've observed here on Earth and throughout our solar system apply universally. This means that the chemistry, physics, and biology we understand are valid everywhere, from the nearest exoplanet to the most distant galaxy. We also have to define what we mean by life. Generally, scientists agree that life is an organized system capable of extracting energy from its environment, using that energy to sustain itself and reproduce. This could range from single-celled organisms all the way up to intelligent beings capable of building civilizations and transmitting signals. It's worth noting though that not everyone agrees with these definitions, and some theories even suggest alternate forms of life that we might not recognize with our current instruments or frameworks. Beyond biological assumptions, we also have to consider cosmological ones. One major assumption is that the parts of the universe we can't see are more or less the same as the parts we can. In other words, the observable universe, a region about 93 billion light-years across, is not unique. There may be vast regions beyond it that follow the same physical laws and are filled with the same types of matter, energy, and processes. This assumption, while untestable directly, is supported by everything we've observed so far. Then comes the idea of cosmic inflation, which posits that in the earliest moments of the universe, space expanded faster than the speed of light, smoothing out any irregularities and creating the large, uniform cosmos we see today. This theory also suggests that our observable universe might just be a small bubble, in a much larger multiverse, an infinite or near-infinite collection of separate universes, each with its own properties and possibly even its own versions of physics. If this is true, then not only is life potentially common in our own universe, but it might also exist in countless other universes that we can never access. Estimates based on inflation theory suggest that the unobservable universe could be at least 400 times larger in radius than what we can currently see. That's a volume about 64 million times greater. If the same laws and conditions apply throughout, then the number of potentially habitable planets increases dramatically, so much so that it becomes harder to imagine a scenario where life doesn't exist somewhere else. But again, the critical limitation is that we can only detect signals from within our own light cone, that is, the region of space from which light or any form of information could have reached us since the Big Bang. Everything outside of that cone, no matter how real or important, remains forever inaccessible to us. So despite our growing understanding of the universe, the true scope of extraterrestrial life remains a cosmic mystery, one we are only just beginning to uncover. Unfortunately, this is the point where we leave behind the comfortable territory of scientific evidence and cross into the gray area of informed speculation. The truth is, science has not yet provided answers to some of the most critical questions about life itself. How exactly does life originate from non-life? What are the specific processes that trigger this incredible transformation? And once life does appear, how often does it stick around? Does it vanish quickly like a spark in the dark, or manage to endure across billions of years like it has on Earth? And if life does manage to survive, does it naturally evolve into more complex, multicellular organisms? Do those organisms often become intelligent, maybe even technologically advanced? If so, how long do such civilizations last before they go extinct, or perhaps wipe themselves out? Right now, we just don't have any direct evidence that answers these questions. That makes it impossible to accurately calculate how often each of these steps occurs. And yet, even in the absence of clear data, human curiosity never rests. We've always speculated and will continue to speculate as long as questions remain. At the moment, the leading scientific theory for how life might emerge from non-life is called peptide RNA coevolution. According to this idea, amino acids, the basic components of proteins, could have spontaneously formed in a watery environment with access to some kind of energy source. The plausibility of this theory is supported by discoveries of water and amino acids in protoplanetary debris like asteroids and comets. These ancient objects contain more than 80 amino acids, some of which don't even exist in Earth biology. And interestingly, they also show variations in chirality or molecular handedness, something that Earth life strictly adheres to. Once amino acids link together into chains called peptides, or essentially primitive proteins, they can begin to carry out basic metabolic functions. Add some ions and you've got yourself a primitive enzyme. Then, if you introduce a kind of nucleic acid, whether that's RNA or other exotic types like PNA or XNA, you've got a system that might be able to replicate itself. Suddenly it's not just a random chemical soup anymore. It's the beginning of life. Of course, this is still very much a theoretical idea. But it's the best starting point we've got for understanding how life might get its first spark. Now we dive even deeper into speculation, and here's where things get really tricky. If we want to put numbers to this, if we want to calculate the odds of life appearing and evolving, we're flying completely blind. Right now, we can't assign reliable probabilities to any of the major steps. From non-life to life, from life to complex organisms, from complexity to intelligence, and from intelligence to advanced technology. We only have one example to work from, and that's Earth. And while Earth tells a hopeful story, it's just one data point in a universe of unknowns. Still, let's walk through Earth's history and imagine each step had a moderate chance of success. Life appeared here fairly early, at least 3.8 billion years ago. Then, after billions of years, it became complex around 600 to 700 million years ago. Eventually, it evolved into intelligent beings. Us. If every one of those steps had, let's say, even a 1% to 10% chance of success on a given planet, then with hundreds of billions or even trillions of planets out there, intelligent life could still be common. But if just one of those steps is extraordinarily rare, say 1 in a billion, then it's entirely possible that we are alone. And that's a sobering thought. It means that, despite the vastness of the cosmos, intelligent life might be incredibly rare, perhaps even unique to Earth. But here's something important. We shouldn't only be looking for intelligent, technologically advanced civilizations. If we were to discover a planet where the smartest creatures were dolphins or even giant spiders, that would be groundbreaking. We would do everything we could to study them, understand them, maybe even communicate. Even discovering a world with simple microbial life would be monumental. It would prove that Earth is not unique, and that life, in some form, exists beyond our tiny blue world. As long as Earth remains the only known home to life, we must entertain the possibility that we are an extraordinary fluke, a cosmic jackpot in the biological lottery. But if we discover even one other example of life, the implications will be huge. That one finding would suggest that the universe might be teeming with life, even if most of it is microscopic or radically different from anything we've ever imagined. It would allow us, finally, to start estimating how many worlds are truly inhabited, and how special or not Earth really is. This brings us to the famous Fermi paradox, the question posed by physicist Enrico Fermi in 1950. Where is everybody? If the ingredients for life are so abundant and the universe so vast, why haven't we seen any evidence of extraterrestrial life? For more than 70 years, scientists have tried to explain this paradox. We know that water, heat, organic molecules, and other essentials for life are everywhere. We know stars and planets form constantly. And yet, silence. As far as hard evidence goes, Earth remains the only place we know of that supports life in any form. To some people that might sound like a pessimistic outlook. Even the legendary Carl Sagan called it an awful waste of space, if we truly are alone. But the lack of evidence hasn't stopped humanity from thinking creatively. Enter Frank Drake, the man who tried to mathematically estimate how many advanced civilizations might be out there. He came up with the now famous Drake equation, a formula designed to multiply together several key variables in order to calculate the number of technologically advanced civilizations in our galaxy that could potentially communicate with us. Drake's equation was nothing short of genius. It asked us to consider things like how often stars form, how many of those stars have planets, how many planets are habitable, how often life arises, how often life becomes intelligent, and so on. Multiply all those factors together and you should, at least in theory, arrive at a number representing how many civilizations are out there right now, broadcasting or listening for signals. It was a revolutionary way of framing the search for life, and for a time, it guided much of our thinking about the cosmos. But as we've learned more about the universe, we've also come to recognize the limitations of the Drake equation. For one, it was formulated before we had solid evidence for the Big Bang, back when the steady-state model of the universe was still considered viable. It also assumed only one planet per star system could support life, which we now know is far from true. Most crucially, it assumed that intelligent life would communicate the way we do, through radio waves. And that assumption has driven decades of SETI research, searching the skies with radio telescopes, for results that have so far come up empty. The problem is, intelligent aliens might not be using radio at all. They could be using something far more advanced, something we haven't even discovered yet. Or they may not want to communicate at all. Maybe they're listening instead. Maybe they're long gone. Or maybe they've simply evolved in ways we can't imagine. So while the original Drake equation was incredibly useful for initiating a scientific framework around these questions, its assumptions have become outdated. In many ways, it has been surpassed by more modern ideas that take into account how little we actually know. But here's the good news. It's now 2023 and our understanding of the galaxy has evolved dramatically. We've discovered thousands of exoplanets. We've found Earth-like worlds in habitable zones. We know that many stars have multiple planets. We've also gained a better understanding of the chemistry and geology needed to support life. All of this means we can start refining our estimates with far more precision than was possible in the 1960s. New frameworks are being developed that incorporate everything from stellar lifespan to planetary atmospheres and even plate tectonics. We're no longer limited to wondering if life exists, we're building the tools to find it. Whether it's microbial organisms beneath Martian soil, plankton-like life in Europa's oceans, or radio signals from an alien civilization 1,000 light-years away, we are now living in an era where discovery is possible. The universe is no longer an abstract canvas of mystery, it's a field of exploration, alive with potential. And we're finally ready to meet it face to face. Back in 1961, scientists asked a simple question. Why estimate how many stars form each year, when we can just count how many there already are? Today we know much more about our galaxy. We've mapped its size, its thickness, the bulge at its center, and how its mass is spread. Thanks to detailed sky surveys, we can confidently say the Milky Way has between 200 and 400 billion stars. Yes, there's still a factor of 2 uncertainty, but that's acceptable. It's a great starting point. And remember, every one of those stars could mean a chance for life. Let's take the high end, 400 billion. The next piece is FP, the fraction of those stars that have planets. We can keep this variable from the original Drake equation. But after the Kepler mission, this part isn't all that mysterious anymore. Why? Because it turns out nearly all stars have planets. Modern surveys show that at least 80% of stars have planetary systems. Many estimates push that number even higher. Some scientists say it's basically 100%. That means almost every star in the Milky Way might have one or more planets orbiting it. So, for our purposes, setting FP to 1 is fair, and very optimistic. Now comes a more interesting question. How many of those stars can support life? That's FH, the fraction of stars with the right conditions for habitability. Our Sun, for example, is a good candidate. It's stable, long-lived, and not too hot or cold. But what about other stars? Massive stars burn through fuel quickly. That might not give life enough time to evolve. Smaller stars live longer, but they can be unstable. Some flare so often they might strip a planet's atmosphere. Others emit too little ultraviolet light. The region of the galaxy matters too. Some zones are chaotic or lack heavy elements. But based on what we know, it's reasonable to say maybe 1 in 4 stars, about 25%, could host habitable planets. Next is NP, the number of potentially habitable worlds per suitable star. Thanks to our study of exoplanets, we've learned a lot. But there are still plenty of questions. What exactly counts as habitable? In the early solar system, Venus, Earth, and Mars all had similar starting points. Even now, places like Europa and Enceladus have subsurface oceans. Those might support life even deep underwater. If a star has gas giants in the right places, their moons could also become interesting. So while we don't have firm answers, it's reasonable to assume each habitable star has one planet with especially good conditions. Let's go with NP equals 1. If we now multiply the first 4 variables, 400 billion stars, FP as 1, FH as 0.25, and NP as 1, we get 100 billion potentially habitable worlds in our galaxy. That's a very exciting number. It's a huge pool of opportunity. So we move on to the next big question. How many of those worlds actually give rise to life? That's FL, the fraction of habitable planets where life begins. This is a tough one. We don't even know for sure how life started on Earth. Maybe it arose here. Maybe it came from space. Some scientists even think life could have started on multiple planets in our solar system. We just don't know. Life might appear often, or be incredibly rare. Optimistically, maybe it happens on 1 out of every 10 habitable worlds. But it could be much rarer, 1 in a million or worse. There's no way to say for sure right now. It's all speculation. For the sake of argument, let's guess 1 in 10,000 habitable planets has life. That's a conservative estimate. But even that would mean 10 million planets in the Milky Way are home to some form of life. That's still mind-blowing. Now let's look at FX, the fraction of those life-harboring worlds where complex life develops. Here we're not talking about bacteria or simple microbes. We're talking about multicellular organisms. Creatures with different tissues, organs, and functions. Even on Earth, this didn't happen right away. It took billions of years. We had the Cambrian explosion only around 500 million years ago. Scientists debate what counts as intelligent, but most agree on what counts as complex. So how often does life go from simple to complex? Let's say 1 in 1,000 times. That would give us around 10,000 planets in the Milky Way filled with diverse, multicellular life forms. If that's true, then we aren't alone in complexity. Somewhere out there, there could be forests, coral reefs, flying creatures, or even entire ecosystems we can't imagine. And some of those planets could be relatively close, maybe just a few hundred light-years away. That brings us to the final variable, Ft, the fraction of those complex life planets that produce intelligent, technologically advanced civilizations. This is perhaps the most difficult one to estimate. It doesn't matter how many times civilizations rise and fall. It doesn't matter what technology they use. What matters is whether they exist now, at the same time as us. There's no evidence of other civilizations right now, so the odds might be very low. Maybe only 1% of those 10,000 planets ever reach this stage. That would mean 100 advanced civilizations. Or maybe it's even rarer. Maybe it's just us. Maybe the odds are 1 in a billion. We can't know yet. But even if the chances are low, the stakes are high. If just one other civilization exists right now, it changes everything. But until we find them, it's all speculation. Those last 3 numbers, FL, FX, and FT, carry the most uncertainty. We may not be able to make accurate estimates yet, but even rough guesses show how much potential the galaxy holds. If we ever find life, just one example beyond Earth, it would be a scientific revolution. Imagine finding a planet filled with plants, animals, or other complex organisms. That would change everything. And if we ever discover intelligent life, someone we can talk to, share knowledge with, or even visit, our view of the universe would never be the same. The truth is, the rewards are enormous. But we'll only unlock them if we keep searching. We must ask, explore, and take those next steps. Some people imagine 2 futures. In one we stay stuck. We argue. We fight. We burn through Earth's resources. And eventually we vanish. That's the sad path, if we never find anyone else out there. No guidance. No connection. No future beyond this planet. Extinction becomes our destiny. But there's another path. A hopeful one. A future where we unite to face the challenges ahead. Climate change. Conflict. Resource scarcity. And maybe, just maybe, a discovery that inspires us. A message, a signal, a civilization far away. That could be the push we need to rise above. Something bigger than ourselves. Until that day comes, all we have is each other. So let's stay curious. Let's keep searching. And let's imagine a better future. Thanks for watching. Subscribe for more videos.